Yeah, go, I guess, like we
Very
can move
much.
to the
Yeah.
next
So
speaker
I
again.
will,
Like,
yeah. I will stop my sharing
yeah,
the,
you stop sharing. So I
yeah.
would kindly ask to Geoff to share the screen if possible. Thank you.
Sorry, that's muted. Can you hear me? Can you see me?
We can see not the presentation mode at the moment.
Can you see it now?
Now we can see the presentation mode and we can also hear you. Thank you.
Okay, thanks. So I'm Geoff Nitschke. I head the Evolutionary Machine Learning Group here in the University of Cape Town, South Africa. So I'll start by saying that most of my work is in the realm of collective behavior. So for the reasons of or complexity associated with many interacting individuals, a lot of our work tends to be in simulation. So it's yet to move into the embodied intelligence domain. But I want to actually look at the social brain hypothesis within collective behavior systems. So as you see here, the social brain hypothesis is that the idea that the big brains we have, or the brain structure that animals currently have in social systems, is due to the need to interact in a social way and to produce, effective social behaviors that better enable the group to survive. So what we wanted to do was to test that within an evolutionary robotics domain, a collective robotics domain. But as you see here on the left side versus the right side, there are two conflicting hypotheses as to what kinds of brain structure and morphology, so we're talking morphology couplings, emerge in different kinds of collective behavior systems. So on the left-hand side, you see that things like, we're just talking about social insects and species and such, we see that things like the division of labor and cooperation are likely driving forces to this increased neuromorphocomplexity. But on the right-hand side, we have another hypothesis which says we see those same types of behavior emerge, group behaviors emerge, but we do not see that increase in neuromorphocomplexity. So we wanted to look at the conditions, the environment and evolutionary conditions that drive neuromorphocomplexity and try and deduce or gain some insight into what those conditions might be. So you'll see there we have an evolutionary robotics domain, and the whole idea is to test this hypothesis that could not normally be tested in ethological studies. So it can never be tested in the real world in terms of a biological study. So you don't need to worry too much about the comparative methods here. So all of my work is based pretty much on evolutionary computation. So we're looking at the evolution of artificial neural networks, which are then plugged into a morphological system. So the idea is, as the neural network becomes more complex, it enables more sensors, and that increases the morphological complexity. So what you see at the top is one of the methods we used, and then an adaptation of that method was NeatM mods. So this is, the idea here is we had two objectives. One objective is to basically do the best job you can, maximize a gathering and a collective gathering task. But you'll see the objective one is to minimize neural complexity. And this was a surrogate, this was a stand-in for the cost of having a big brain. The idea is more complex networks use more energy, so we need more, they're more expensive to keep. And you'll see there at the bottom, we have neural complexity is just a function of the number of neurons connected in the network. So these are like the individuals in our task, right? So we have robots moving around and they have to accomplish some task. But as I said before, the number of sensors that are active increases the morphological complexity, and that in turn, or is driven by increases in the neural complexity. So basically we have a neural network connected with a number of connections and nodes in between connecting all of those sensors. And as this increases in complexity, so does the morphological complexity. So that's what we have here. So it's basically the number of sensors connecting with a network, and this drives up morphological complexity as neural complexity increases. Okay, so this is just a snapshot and illustration of what's going on here. So you'll see on the top right-hand side, it's like a collective behavior box pushing task. And the key idea was we could tune the complexity of the task by requiring that more robots cooperate in order to push a box. So a larger box would need to be pushed by 3 versus 2 robots, something like that. So we could tune the complexity of the task and see what kind of neuromorphocomplexity emerged as a result. So if we just compare our two methods, so the one with the complexity cost basically, and the one without the complexity cost, and it's defined as neural simplicity, which you see on the left-hand side on the y-axis, you'll see that maybe not surprisingly, with the complexity cost, we got simpler networks, right? Which is what you pretty much would expect. But if you just look at the task performance, so basically how many boxes they collected in cooperatively and moved to one area of the environment, you'll see that the method with neural complexity cost versus without neural complexity cost basically yielded the same task performance. So this gives us the idea that simpler networks are just as beneficial as more complex networks, but it is the interaction of those networks that drives up task performance. So this is supported by related work, which shows that basically you don't need a whole lot of neural complexity, but it's rather the interaction of relatively simple networks that promote or create the overall task performance at the group level. And the second study that I want to look at very briefly is in a similar vein of work, but it did not have the neural complexity cost. So it's the same idea where you had a whole bunch of robots in the task domain. They had to gather some objects, and task complexity was tuned by how many robots required to push objects. So we had morphocomplexity being involved in some task environment. And once again, you just had the task being tuned, or the task complexity being tuned by the number of robots required to push given objects. So we could nicely divide it into simple, medium, and difficult task environments, and to see what kind of neuromorphic complexity emerged as a result. So once again, I'm not going to go into detail about these methods. You don't need to know too much about them. But the important point is you'll see EDQM, which was just morphological adaptation. So it was adapting like the number of sensors active, the average range of the sensors. And so this was directly related to the underlying neural complexity. And then the one below double map EDQDM was co-evolving behavior and morphology, right? So we wanted to look at kind of, if we just have these comparative methods, what kinds of neuromorpho complexity emerged as a result of being given this task in this task environment. So what you see on the left-hand side on the y-axis is the neuromorpho complexity. So 1 is the most complex, 0 is the least complex, and you'll see the metric MC is the morpho complexity metric. But the interesting part is, if you look at the purple, the double map EDQDM, this achieves across all task complexity. As we increase task complexity, the neural complexity remains relatively low compared to the other methods. So this suggests that adapting morphology in company with the behavior is advantageous, not just then it produces high task performance, but it produces consistently low complexity, but relies on the interaction of those agents to produce the high task performance. And we see this also if we look at basically the spread of behaviors evolved across task environments. So what you're looking at is the quality diversity score, which is basically just a map. So it says for any given behavior, what is the quality versus its diversity? So how different is it from other behaviors? So you'll see that the evolution of morphology and behavior consistently produce very high quality and very diverse behaviors, given an indication that's nicely exploring the behavior space, versus the other methods that we tested. So what does this tell us overall? So what is nice about these experiments is they can show us something about the conditions, the evolutionary and the environmental conditions that lead to these types of behavior morphology complexities. And this is supported by related work, which basically says that neural complexity is good up to a point, and then it becomes redundant, especially in collective behavior systems where monopolizing or leveraging the interaction between individuals is really key. It's really important. So in terms of future work, there's a lot to be done. Of course, you'll see they're embodied systems. So actually evaluating this in real swarm robotic systems, real embodied intelligence platforms would be really valuable. And to try and then use other metrics. So the metrics we use for complexity were pretty simple, but there are other metrics out there like information theory metrics and so on and so forth that are more in line with metrics used in neuroscience. that could be really valuable, and also looking at other body-brain adaptation methods as well that we theorize may work well for these evolutionary robotics platforms. And yeah, that is all I have. I'd like to thank everyone who was involved in these studies, and yeah, thanks again.
Thank you so much, Geoff. Great talk. And again, please write question in the chat so we can discuss later in the panel discussion. And I would ask